Thank you everyone for coming today to join us on this fourth session of Road to Research Meet the Researcher. Our presenter today is going to be Rebecca Gruener. She is a mechanical engineering PhD candidate. She's a researcher and she is working with the Center for Atmospheric and Particle Studies, also known as CAPS, here on campus. So Rebecca, if you would like to advance the next slide, please. Thank you. So like I said, we'll get to know her, learn about her experiences in middle school, her experiences in high school, and what sort of brought her to college and then to CMU to be doing the air pollution research that she's doing now. We'll break out into our breakout sessions, and then we'll come back for our conclusion at the end. So next slide, please, Rebecca. I believe everybody already knows who I am. I'm Kristen Lavery. I'm the LGC Assistant Director and Business Manager. I've been with the center for almost 8 years. And while in grad school, I worked as a substitute teacher and I did wedding photography on the weekends. And also today is my best friend Odin's 10th birthday. He's a Norwegian elk hound. And when he's happy, he makes Wookiee-like sounds, so he kind of sounds like Chewbacca when he's excited. The next person who's part of our coordination team is Dr. Vicki Webster Wood. She's an assistant professor in mechanical engineering. Vicki, if you'd like to say a few words about yourself.
Thanks, Kristen. Welcome back, everybody. I am, like Kristen said, Dr. Webster Wood, and I run the Biohybrid and Organic Robotics Group at Carnegie Mellon. For those of you who have been here before and know me, you may remember that I have two enormous shepherds, one German Shepherd, one Belgian Malinois. We talked about some of these points last week, but in addition to these, the one I was joking about this week is that I am a Cleveland Browns fan, but I redeem myself by being a Pittsburgh Penguins fan because hockey is the best sport. And with that, many of you may also already know the next member of our coordination team, Saul Schaefer. And Saul, do you want to take a second to introduce yourself?
Sure. Hey, everybody. I'm Saul. I am a PhD candidate now in Vicki's lab, the Biohybrid and Organic Robotics Group. I own my own CMU blanket and scarf that was made by a friend of mine, which is very kind of them. In my free time, I love to bike around Shenley and make hummus at home. I got a nice food processor pretty much explicitly for that purpose. And for Halloween, I used my baldness to my advantage and was Avatar Aang as my costume. So that was a lot of fun. Can we go to the next slide? All right, fantastic. So, this one. So now we're gonna go around and have all of the mentors today introduce themselves. They're going to share their names, their majors, and then what they're researching, as well as one fun fact about themselves. So let's do it in the order that it shows up in my chat. So let's do Joe first.
There we go. Hey, everybody. I'm Joe. I am a fifth-year PhD candidate. I work on robots. Last time I talked about my cats. But this time I'll say, growing up, I'm from Minnesota, and my favorite baseball team was the Minnesota Twins, which is ironic because I have a twin. So I am a Minnesota Twin. That's it.
That's a good one. Let's go next, Julian.
Hi, I'm Julian. I'm a fifth-year PhD student in mechanical engineering and robotics, and I work on modular robots and using artificial intelligence to make robots move around. I do not have a lot of fun, but I do like to spend a couple minutes each day in the morning and the evening petting my guinea pigs, taking care of them. They're small and they're furry.
Wonderful. All righty, Kathleen.
Hi, I'm Kathleen. And I am a mechanical engineering PhD student, and my favorite thing to paint is the ocean.
Great. All right, Purva.
Hi, I'm Purva. I'm a fourth-year PhD candidate, and I love engineering as much as I love medicine. So I'm working on organ preservation, and I love dogs and love to go on hikes. And when I'm worried, I love to clean my house.
Fantastic. All right, Terry.
Hi, I'm Terry. Oops, that was also supposed to be video. Hi, I'm Terry. I'm a second-year PhD student in the robotics department, and I work on research to recreate whiskers found in animals for robots. And I like to knit, and when I got to go travel and see cool places, I collect keychains from everywhere I've been.
Very cool. All right, I think that's all of our mentors. So now we will have Rebecca tell us a little bit about herself, or let's introduce Rebecca, our speaker for today, who is a PhD student, or a PhD candidate, who's doing lots of very interesting stuff with air pollution. Rebecca, do you want to turn on your video and mic? We're gonna ask you a few questions, get to know you a little bit.
Yeah, hey.
Hello. All righty. So could you go to the next slide?
Yeah. Wait. Yeah, there we go. Okay, so I guess.
Yeah, so I mean, I can ask you a question, or you can sort of start. Totally up to you.
Yeah, I guess I'll just jump in and start by introducing myself. Like you heard already, my name's Rebecca. I'm originally from New York. So here's New York State. I'm from Long Island, a town called Oceanside. So if you zoom into the red dot on the first map, then there's Nassau County and there's Oceanside. And if you haven't heard of Oceanside, which I wouldn't expect people to have, it might not sound so exciting, but actually growing up there was pretty cool because I was a 40-minute train ride from New York City. So it's pretty common for, people in my town to be able to go into Manhattan, like on the weekends. A lot of people's parents work in the city. So it was an exciting place to grow up. Also, Oceanside, as it sounds like in the name, is really close to the ocean, which is also probably sounds exciting for people that, you guys are growing up in Pittsburgh. Maybe some of you haven't even been to the ocean because we're not super close over here. So I grew up like 10 minutes away from like the Atlantic Ocean, would spend a lot of time on this boardwalk. I even rode my bike there once. So pretty cool place to be. But I'll start off with, sort of talking about my experiences in middle school and, how they shaped where I am today. So here's one of the least offensive pictures of me in middle school, and it's really still not a great picture. But I think my family had a lot of fun when I asked them to send me a picture from my parents' house of me in middle school, and my little sister sent me like a bunch of really horrible pictures. So this was the first one that I was like, okay, I guess I could share this. So me in middle school. So what are some of the things I was interested in? I certainly didn't know I wanted to be an engineer or a scientist at that point, but here's my middle school, a picture of the front door. Probably looks similar to a lot of your middle schools. But I really liked all sort of subjects. I liked reading. I remember my English class. I think I spoke to some people in the last session about books people read, and I remember my favorite book from middle school was The Giver, and I remember some people also liked that from my little breakout room. I really liked my biology class because in 8th grade I got to take high school science. In New York we take Regents tests, which I'm sure you have something similar in Pennsylvania, but they're basically high school exams. So I got to take the high school test in middle school, so I was pretty into bio at that time. I also really liked technology. It was a specific course called technology, where we got to like learn about computers and also like do some wood shop basically, where we like crafted a little car out of a block of wood. It was small, but then we raced them. So that was probably my first interaction with anything related to engineering, but I didn't know that it was engineering at the time. No one said that, you know, this sort of involves some aspects of engineering, but it was just like cool to get to race these little cars. But I also really liked home ec, and basically I certainly did not know what I wanted to do when I was in middle school, but I liked school. And okay, oh wait, I need to click back here, the advance. Oh, there. So one thing that sort of stands out that I think also connects to like where I am today is I started taking this class called Math Research, where it was a research-based class starting in 7th grade, where you got to pick a topic that you don't learn in school and research it in depth. And then ultimately you get to bring that research topic to a math fair and present it in front of judges from all over Long Island. And then you get to be evaluated and judged, and people move on to the next round and get to do it another time. And basically I did math research, not only in middle school, I did it all the way through graduating high school, and I got gold medals every year. It was great. So I really liked research in that sense. My research now is a little different, but I guess that was my first taste of research. And it was fun to win medals, but it's not all about winning medals, but it was a good bonus. I wasn't all about, you know, classes and, you know, math. I was involved in the Oceanside Middle School cheerleading team. And I also really enjoyed dance. I danced a lot of time outside of school and did, you know, like competitive dance through my studio. So those were sort of like what sums me up in middle school. Is that, Saul, what do you think?
Yeah, I think that's all great. You sort of answered all the questions I was going to ask. Other than maybe, do you think that your experiences in middle school like sort of shaped the trajectory of where you ended up going career-wise, academically?
Yeah, I think like I sort of hinted to there is that I think the math research was maybe the first like seeds planted towards me wanting to do research, although I might not have really realized it then. And that coupled with also enjoying those like technology classes where I got to build little cars, and, you know, sort of those are maybe the first places where I was introduced to things that all, you know, I ended up following through with. But really I enjoyed school. I enjoyed my extracurriculars. Oh, I think I also had one more extracurricular. I did Builders Club, which was the Kiwanis Club. Maybe some of you are involved with Builders Club in your schools. So I really liked community service. I really liked dancing, being active, but I did really like my classes too. So yeah.
Awesome.
Yeah. So I guess I'll move on.
Yeah, next slide is great.
High school. Yeah, so I think high school was at first, you know, it's a big adjustment going from like the middle school. It's much small, like it's only 2 grades, less people, into the high school where all of a sudden you're thrown in with, as a little 9th grader, you feel pretty small compared to some of the 12th graders. But I think like as high school went on, I got into my groove. That's my high school, Oceanside High School. I like continued to like pursue similar passions, like kept dancing outside of school, took up more time as I got older. So that was like definitely a focal point of my like high school experience. Also outside of school, there's me like hanging out at the beach because again, Oceanside, friends would just like go hang out on the lifeguard chairs when, you know, it was after hours. So really enjoying being outside. Side note, like I feel like I really like got like, you know, got more comfortable with myself when I, you know, by the time I got into 10th grade, I got involved with like clubs outside of school. Like there was a youth group that I got to go on like international trip with one of the summers, and it just like gave me a lot of confidence. There's me involved in like some like community activist groups. And also that was Key Club, that last picture there. So involved with very similar things as I was involved with in middle school, but like to maybe like an amplified extent. So I think like high school is a cool time to, you know, explore your interests outside of class, as well as of course in class. So when I think of my favorite classes in high school, I think of one of my English classes, where we got to read really interesting stories, but probably one of the most exciting parts was that the teacher was really passionate about writing and creative writing, and would really push like me and my classmates to like write creatively and think outside the box. And that was really exciting. I got to take more creative writing classes. I really loved taking French, and got to take like AP French. And I really, then on the sciences and math side, I really enjoyed chemistry. And for a time, I think I thought about going into like more that might have been like the first sort of spark of interest in like more serious research, because I remember taking chemistry and really being enthralled by like molecules and the idea of like, you know, drug discovery, like for medicines. So that seemed really interesting to me. So I was really all over the place in interests, but really liked school. And I really enjoyed my like calculus classes. So again, really liking math and science. And I stuck with math research. And yeah, so those were like pretty much highlights. If I think of my least favorite classes, they were gym and ceramics, which for some people, those might be people's favorite classes, but I always had like an excuse to get out of gym. Maybe that's not a great thing to say, but I was involved in a lot of clubs, and there was always a bake sale that I was running, or, you know, something else that I had to go do. And my gym teachers were very, you know, I guess they were very like able to be convinced that that those were valid excuses to not be there. So that was pretty great, because I didn't really like gym, so I didn't have to be there much. And then classes that I was like so about was definitely physics. And I think that that's interesting, because I remember struggling with physics at first and being really frustrated by it, because a lot of physics is dealing with like forces and motion. And it's funny because as an engineer, specifically as a mechanical engineer, physics is like the basis of almost all of my coursework, like in college. So it's funny looking back that at first I wasn't really too happy with physics, and I didn't really enjoy learning it. But I think once I sort of like got the knack of it more, I saw that physics is everywhere, and it's pretty cool to be able to understand how so much of the world around us functions. So I think that's what sort of made me more excited about physics and eventually go towards engineering. But yeah, in all, I think high school is a really cool time to like explore different subjects. You still get to take a lot of different classes, but really important to focus on those extracurriculars, because those help you discover really who you are outside of the classroom and can help guide you towards what you want to do in college as well. So here's just like a laundry list of things that I was super involved with in high school as well. Yeah.
On that list, I see mathletes. What got you interested in this club?
Yeah, I don't remember what got me interested in the first place, but it was a cool club. It wasn't super big, and we also got to compete. I guess I'm very competitive, so I liked the idea of going to competitions and potentially like winning prizes. We did not win prizes. My mathlete team was not super good, but it was nice to like make those connections with people. And it was like a small group of people and a pretty chill teacher who ran it. So we got to hang out, you know, once a week and practice interesting math problems. And then we eventually got to go to competitions where we did not do well, but you know, it was an experience all around.
Yeah, that sounds like a lot of fun.
Yeah.
So you sort of described really enjoying chemistry and sort of that's sparking your interest in like the environment and engineering. How did that sort of translate into college, what you studied and what you did?
Yeah, so when I got to college, I was, let's advance. So when I got to college, when I applied to college, I was still pretty undecided. I wanted to go in undecided, which is totally something you can do. You don't need to know when you first get to college what you want to do. But I basically the summer, or I took a gap year. So I like graduated high school, and then I had a year where I wasn't, in the States. I went abroad, and I had time to think about more what I wanted to do in college. And I realized that people, people tend to say if you like math and science, you should keep doing math and science. So you guys all, it seems like you like science if you're here, so you should keep doing math and science. But people told me that, and they tend to say either go into like medicine or engineering, and I just really had no desire to go into medicine. I didn't want to, see the insides of people. No desire there. So I was like, well, I guess the other path people keep saying is engineering. So what's engineering? I got to college and I didn't really know what engineering was still. And like, I just continued to sort of like cultivate my other interests. I also took, more general classes like histories and general requirements. I kept up my extracurriculars. I kept dancing in college. There's a picture, super fun. I also started teaching group fitness classes there. So college is a great time to grow and discover things that you're interested in and like cultivate existing passions, even outside of coursework. But eventually I was sort of pushed to, you have to make a decision. So I was pushed towards engineering because I was like, well, yeah, I still like this math and science stuff. I want to help people. I want to help the world solve interesting problems. And it seems like engineers are really able to solve so many different types of problems. And why I chose mechanical engineering, which is super physics based. So at that point, I guess I had like changed my mind about physics, but mechanical engineering is pretty broad as far as the different engineering like majors go. So I felt like I could do that without really making a decision of what I wanted to be yet. So I could go into mechanical engineering and still have a lot of options open to me when I graduated. I didn't want to just like pigeonhole myself. So I did engineering, and after my sophomore year, I think I still didn't really know what an engineer was because I was just taking classes.
Real quick, we got a question in the chat asking which college you went to for undergrad.
Oh yeah, I went to Binghamton University. It's State University of New York, so it's upstate New York. It's like 5 hours from here. It's 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 a cool place. It's really fun like area to live in for college because there's not much around. So like there's not many distractions outside of the university. So everyone really like all your activities are all on the campus. So that's pretty nice, but like it's a pretty quiet town outside of the university. But yeah, question. So yeah, so went to Binghamton, 2 years of engineering classes, still didn't really know what an engineer did, certainly not a mechanical engineer. And then I got my first internship, my summer internship at NASA. So that was really exciting. It was at the NASA Langley facility in Virginia. And that was the first time I got to actually see what real life engineers do. And I'm like looking at the chat popping up there. Okay, cool. Yeah, so I got to see what engineers do, and I got some hands-on experience. We were working with cube satellites, which are little satellites like the size of a football that they're able to send up into space for like different science experiments, like different research that you could do much faster and cheaper because it's on this small little satellite instead of like a huge satellite. So I got to actually design like aspects of this cube satellite, and I got to 3D print. For those of you who went to Saul's session, learned a lot about 3D printing. but I got to 3D print parts for my little CubeSat, and then eventually make a model, print a whole model of my CubeSat with that I designed. And that's me and my mentor at NASA, and he was super cool, as you could see from the picture. We're just goofing around, but I got to see what researchers do and what engineers do, and I really liked the environment, and I liked how everyone there was sort of just interested in solving problems, and they would have these questions and be able to just dedicate time to think about the answers and figure out ways to solve things in new ways. And I thought that was such an exciting world to be in. So I really liked the research experience. But then after my junior year in college, I wanted to get industry experience. Saul, you have a question?
Yes, I got a question from the chat. Someone asked, how would you launch the satellite?
Yeah, so these little satellites get payloads on larger launches. So they sort of tag along on a big satellite or a bigger mission. If you have something going to the International Space Station, they'll sort of tag along and then be dropped off into space. Yeah, sadly, my CubeSat never ended up being launched, but it was still that's also research, because sometimes people work on things in research and they don't work out, but that's part of the discovery process. But it was pretty cool. But basically, after that, I wanted to have an industry experience, because there's research and then there's working for out in a company. So I got a job at a small startup for the summer after junior year, where they were working on making changing over boilers and sort of energy saving. I did not love the internship, even though they sent me to this little day-long conference at National Grid, which was cool, but I didn't love the internship. And that is what probably pushed me to pursue more research experiences, because since I didn't love that internship, I got another internship, and this is just a pile of garbage, but in this picture, but it's because my next research internship involved looking into ways to convert waste to energy, and the lab I was working in went on a field trip to this waste to energy site, and I took a picture of a pile of garbage because I thought it was cool. But yeah, I just basically, between those 2 summers, I figured out, hey, I don't think I want to go into industry right now. I think I really like research. So by the time I graduated Binghamton, I knew, well, I guess before I graduated, because you have to apply a little bit before you graduate, but I started to apply to graduate schools because I knew that if I want to do research, then I want to have a PhD to do the research, because you could do research in a lot of different ways, but if you have a PhD, that's probably the most clear path to get to do the research you want to do. There are a lot of routes, but I figured that was a good route for me. And I went straight from undergrad to graduate school here at Carnegie Mellon in Pittsburgh. So here I am. That was my first day of grad school, back when I did Snapchat. I don't know, is Snapchat still cool? I don't use it really much anymore. But 4 years ago, I was really into Snapchat, so there was a snap there. But yeah. So,
what made you choose CMU for your PhD?
Yeah, so like I said, that other research experience that wasn't at NASA, the one after that, was waste to energy. So I was looking at emissions from sort of landfill gases. So I was sort of in that realm of emissions. And I was looking at grad schools, and the way grad school works a lot of the time is you look for professors that are doing really cool work, and you say hey, I think I'd like to work with that professor, and then you apply to the school. So I was looking for mostly professors that were somewhere in the realm of emissions or pollution, or I wanted to mitigate pollution, or something with clean energy, something in that world. I wasn't super specific. I also didn't want to go too far from New York because I had family there, and the location. So I was sort of important. So I sort of drew a circle around New York. I'm how far am I willing to go? And Pittsburgh was in that circle. It was actually just barely in that circle, but then I came and visited CMU. I was okay, fine. it's really good. It seems like a really awesome program. It's okay that it's like 7 hours away from Oceanside, but yeah. So I got to grad school, and this is what my desk looked like when I first started. It was super clean and empty, and actually the whole space was like totally brand new. So no one even the next desk next to me was empty. And then by the end of that semester, this is what my desk looked like. As you can see, like really jumped into work here. There's a lot, a lot to do, a lot to study. But really like interesting stuff. Like in grad school, you get to take classes that are super specific to what you're studying. So I was taking a lot of like air quality classes and trying to learn how to do research. And my first, oops there. Oh, that wasn't supposed to pop up yet. Maybe it is. Okay, that'll pop up next. I got to, so over the course of time doing research here at CMU, I've gotten to do a lot of different things. So we'll dive into the specifics of my research later, but I just want to show you in a few pictures what like my day looks like. So I've done projects where I've actually driven around in this van and measured pollutants with like really interesting instruments and get a sense of what the air quality is like all throughout the city and how it changes over time and space. And let me tell you, driving, you guys don't drive yet. Driving, big responsibility, but you get used to it eventually. Driving a big van with a bunch of instruments in it, really scary. So it was so big, and I might have hit a garbage can once, but it was fine. So that was definitely challenging. But yeah, my day-to-day work is really varied. I've gotten to do a lot of field work where I put sensors out at people's houses and parks and public spaces. And actually that work was featured on a children's science TV show. And that man there standing next to me is Jacques Cousteau's grandson. If you know who Jacques Cousteau is, he was like famous like for documentaries and stuff. So that's his grandson, Philippe Cousteau, who hosts this children's science TV show, and they featured my lab on it. So I got to be on it. So that was pretty awesome. Definitely a highlight of my grad school experience. I've also learned to fly a drone because we needed to take measurements of the wind, because the wind, the way it's blowing at ground level is different than how it is up high, and how the wind blows affects how pollutants move and change over time. So in order to get a really good understanding of what's going on with the wind, we needed to get measurements at different heights. So we bought a drone. I got to learn how to fly it. Someone else in my lab crashed it a few times, but thankfully I did not crash it at all. So I might have scratched the van, but I did not crash the drone. So that was all good, but definitely a really interesting experience. Some of my work has moved inside a little bit more. If you can't tell, that's a recent picture because mask, but I get to do lab work inside the lab and get to use really interesting instruments to measure pollutants that are emitted from different sources. And I'll talk a little bit about that later, but I really love that my work has taken me like outside, inside, different weather, like all these different things. I also spend a lot of time crunching numbers in front of a computer, but like I said, I like math, so that's pretty cool too. I got to last summer was a highlight. I got to, not this past one, like 2020, but 2019, I got to do an internship because of grad school at the U.S. Environmental Protection Agency. So got to work at the EPA for a summer and measured different types of pollutants there. Also last summer, side note, highlight of grad school, got married. Just want to throw that one in there because it's a fun picture. But yeah, so I mean, I guess my point is that grad school is pretty interesting. You solve pretty cool problems, but you have a life outside of work too. So that's great. And yeah, I'd say just overall, I've really enjoyed my grad school experience because this is a picture of the Coke plant in Clarendon emitting a lot of pollutants. And this like impacts real people and like on their day-to-day life. And I get to do work that'll hopefully make their lives better and healthier. So it's been pretty cool. any questions popping up there?
From the chat, not so much. That was all such great information. Something that I've got though is, was there anything from your gap year that sort of shaped your college interest that then sort of transitioned you into graduate school?
I'd say maybe not something in particular, but just like having some time to think a little bit more about, well, what do I want to do? I do remember doing some Google searches, like I want to use math and science to help people, like help humanity, but not like necessarily like touch individual people, like, you know, so it was like not the like medical field or like individual helping field. I wanted to like help people in general. And then like those Google searches sort of led me to engineers. They do a lot of societal good. So that pushed me towards choosing engineering.
Well, I think that's a perfect segue to talk about your research. So I'm going to transfer over to Kristen, who's going to take over.
Mm-hmm.
All right. Thank you, Saul. It's great to hear about your background, Rebecca, and that even personally, I like the parts where even when you weren't so sure about what you wanted to have be your end goal, you remained curious about science in general.
Mm-hmm.
Probably one of the favorite things. So, what's the matter with particulate matter? We're going to delve into your research a little bit more, and we're going to start off by having our first poll. And that poll question is going to be, what is an aerosol? I'm going to launch polling here now. And an aerosol, is it A, a solid or liquid suspended in a gas, B, my hairspray container, or C, a particle in water? So I'll give you all just a moment or two more to answer. And if you can't see the poll, feel free to type your answer into the chat if you would like. And our options are A, a solid or liquid suspended in gas, B, my hairspray container, or C, a particle in water. And this answer is multiple choice.
Kristen, we've got a question in chat. Is the hairspray container the container or the hairspray inside the container?
So Rebecca, what did you?
You could go with either.
Okay, so we'll find out the full answer in just a moment here.
Your hairspray container might be a really big aerosol. It's a spoiler.
Okay, I'm going to end polling and share the results here. So most of our participants said A. Some said B, and a few said C. So Rebecca, would you explain that for us?
Yeah, so I think we'll get to the actual definition in like a few slides, but the general idea, A is the most correct answer. A is the correct answer, although your hairspray container, you know, the insides of your hairspray container are also aerosols or become aerosols. And your hairspray container could be a really big aerosol, but I'll get to explaining why, I guess, in a bit. Maybe the next slide. Yeah.
Stay tuned for more, I guess.
Yeah. So let's talk about aerosols. So some people, when they hear aerosols, think of Hairspray, and maybe not the movie, but if you haven't seen the movie, highly recommend. Great movie, and great music. But even my parents, I think, like now, I guess like I've talked enough about my research that they don't make this joke anymore, but they do send me pictures of like hairspray cans and stuff. Because I think like in a common sense, like when we say the word aerosol, and maybe this has changed recently with COVID. It probably has changed because people have probably heard the word aerosol a lot more. But I think before, people probably think of hairspray or like, aerosol cans, like, oh, that's, the stuff coming out is an aerosol. But what really is an aerosol? We'll see. Oh, no, wait, okay. I thought I had a definition there. Wait, I might just, wait, where do you, I'm gonna jump to, no. Okay.
Do you want to do the second poll?
No, we'll wait on the second poll. That
Okay.
an aerosol is basically a solid or liquid particle that is suspended in a gas. So that's why I was sort of joking that your aerosol can might be a really big aerosol, because if you could get it suspended in a gas, it is solid, right? So it's, but generally they're, really small, pieces of either liquid or solid that are like floating around. And like I said, you probably heard the word aerosol a lot in terms of COVID recently, because we talk a lot about the spread of COVID through aerosols, which are like generated when you're speaking or when you sneeze. And those are little pieces of, your spit or snot that might contain viruses that are then suspended in the gas around. So now next time you hear someone, talk about how COVID is spread, you could say, hey, it's spread largely in aerosol particles. But this will bring us to our next question, which let's talk a little bit more about aerosols and where do you think they come from? is just the general question, which maybe I gave it away in that explanation.
Yeah. So where do you think aerosols come from is our poll question. And we have answers A, humans, B, plants, and C, industry. And this one is also multiple choice as well.
And while people are filling that out, Rebecca, we've got a question in the chat. What gas would a hairspray be suspended in?
That's a good question. Oh, no, okay. The gas it's suspended in is actually it's just talking about that gas all around us, so oxygen, nitrogen, just whatever's in the atmosphere around, that's the gas that it's suspended in. So the aerosol is the mixture of a particle in some gas. So anytime you have a particle floating around you, the gas is all the atmosphere around you, if that makes sense.
Oh, not the spray itself. Sorry, I misinterpreted the question. What gas would it take to suspend the can?
Oh, okay, I don't know. I guess something that would be able to sort of float around in, I don't know. Maybe if you put it on the moon and then it was light enough to sort of suspend around.
So it would have to be a really dense gas in really low gravity.
Yeah.
Awesome. And there was one last question before I let Kristen get on with the poll. Could a feather count as an aerosol if it floats in the air?
Yeah, these are fun questions. It's sort of I guess different to think about, because really we really do think of small particles, micrometer particles. So yeah, I think probably not. but maybe people would have different definitions.
All right, so I'm going to go ahead and end our polling now and share the results.
Yeah, so it looks like industry is the winner here, but we have some votes for humans and plants. And honestly, the truth is that you're all right, that it was a trick question. All of these things, people, factories, different industry applications, as well as forests and just plants, will emit particles that will then be suspended in air and form aerosols. So from all these things. Yeah. So we'll move on. So aerosol particles come from different sources. So like as I sort of started to say, and you got from that poll, is that, you know, aerosols come from a lot of different things. So, you know, you could think of vehicles that are out on the road, and this is a really, really sort of gross, bad example. This truck, you see these like huge puffs of smoke coming out of its exhaust. Thankfully, most cars and vehicles on the road don't look like that, but that is certainly generating particles that will be suspended in the air. And actually, when you think of vehicles, they're not only emitting from their tailpipe pollutants, they also, their tires will like wear on the road, and those will create like coarser, bigger particles that can also be like suspended in air to create aerosols. That's one really big source, and something that people have thought about for a while now, or like how much do vehicles emit. But then we also have like biogenic emissions. So that's a cool word. Biogenic means it comes from, you know, like biological sources. So it's not people made. So you have VOCs, or like volatile organic compounds, which are emitted from plants and from forests. And those organic compounds will have a lot of really interesting reactions in the atmosphere to form particles that then will be suspended in the air. So that's an interesting source. You probably don't think of, you know, forests as a place where something is being emitted from, but it is. And then unfortunately, forests sometimes turn into forest fires, and then that is a pretty big source of emissions. A lot of, you know, bad soot and, you know, different chemicals being emitted, forming particles. And not only do you have like particles being emitted, you also have gases that will then again react with other gases and become particles themselves. So a lot of stuff being emitted from that. Here's a local picture. I took this one. It's of the Clarendon Coke plant, which I'll talk about a lot. They're a pretty big emitter here in this area. But there you could see a stack of, you know, emissions coming out. Honestly, sometimes when you see like stuff coming out of factories, it might be fine, because a lot of the time it's just water vapor. So if it's mostly white, it might not actually be like emitting, you know, hazardous pollutants, but sometimes they also are. So like, you know, you gotta take the picture with a grain of salt, but they are emitting particles there. So that's factories. Also, sea spray is another source of aerosols. So that's an interesting one. As you know, waves crash, you get like calcium deposits that are then like emitted, and will have interesting reactions. Also, cooking. Here's a picture of a cook stove, which actually millions of people all around the world actually, you know, the way they get their dinner at night is using like indoor cook stoves, which are really high emitters of particles, and it's really a contributor to a lot of like health problems throughout the world. So a lot of people are trying to work on ways to help people be able to make food affordably, but like safer. But not just stoves emit.
And those stoves, Rebecca, they look like they use some sort of like wood or maybe charcoal.
Yeah, a lot of them will use wood, and you'll just like cook in your house, and like sometimes people don't have great, you know, ventilation in their living area where they're cooking, so then they're breathing all that in. So it's a problem in a lot of parts of the world. But not just that type of cooking, even here in Pittsburgh, when you think of big restaurants, some of them are really high emitters of particles. So it's an interesting thing to think about. And then we also have, you know, people make aerosols. So that's a very relevant picture. There's someone, you know, sneezing, coughing, he needs a mask. But, you know, we'll emit particles as we're speaking, and, you know, those are very different than some of these others that we talked about. But here's like sort of one of the take-home points here, to sort of differentiate what I'm talking about. So aerosols, like I said before, this was the big definition. Aerosols are liquids or solid particles that are surrounded in a gas. So it's like it's both parts. When you hear aerosol, so next time someone talks about, COVID and aerosols, or your hairspray and aerosols, you'll know what they mean. It's basically the solid particle or the liquid particle and the gas. Whereas particulate matter, which is another term that I'm going to use a lot moving forward, it's just the particles. So it's like the same particles, but one is talking about the particles and the gas, and one is just talking about the particles. So now we're on the same page with that. We can move forward.
So why do we need to study these particles and particulate matter?
Yeah, that's a good question. So we want to study them because we really don't know a lot about them still. we've gained a lot of knowledge, but really not all particles, like I wrote here, are created equal. There are so many differences in these different particles. And you can imagine you have all this stuff in the air that we're breathing. You want to know what that is. So different particles have very different sizes. So they range in size. They range in chemical composition. Like, as you can imagine, something coming from your mouth is very different than, what's coming from sea spray. So that means they like react with things in the atmosphere differently and will cause other like different sort of reactions. They have different shapes, which also changes how they react with things in the atmosphere. And you can have different mixtures of things. So there's so many different things that you can, have in one particle, that in order to understand like the overall effect of what is in the atmosphere, you have to take a lot of measurements and do a lot of like chemistry to understand what's going on. And so one thing, we'll get to I know someone asked about health, and we'll get to that, but I think one of the big things, or the biggest sort of questions around particles, is how they affect what's called radiative forcing, which is basically how the sun interacts with our atmosphere and with us down here on Earth. So you have the sun, emitting radiation, and it gets, blocked to a certain extent in our atmosphere, and then a certain amount comes down and, hits Earth and warms Earth and provides nutrients for plants and all this good stuff. But when you put particles out into the atmosphere, it changes that sort of balance and like how things work. So when you have particles out there, you could see that some of them will just absorb the sunlight and not let it like hit directly Earth the way it would have before. And some particles will scatter light. And this changes, the amount of sunlight that we're getting down here. So it changes the radiative forcing. That's the direct way that particles can sort of impact that. And then there's an indirect way that particles can also cause water vapor to condense onto them. And that's where clouds form. So you end up creating different types of clouds based on what particles you are starting with. So that will also change how much sunlight like gets down to Earth, whether it's more or less. And we have a lot of questions about which particles will basically like cool or warm the Earth. And if this is maybe like lights are going off in your head thinking like, oh, maybe all these particles have an effect on climate change. So that's really one of the biggest reasons why we need to study particulate matter, to understand which particles are causing what types of changes. And climate change sounds like this really, abstract sort of problem, but we can break it down in a few like pictures of like, what does climate change mean? So here's a picture of me in New Zealand. It was a super cool trip. I did a lot of hiking, but you could see that like I'm standing here with this sign, and I don't know if you could read it, but the sign says that in 2009, the glacier ended here. So if you look all the way back, like way back in the picture, there's a glacier. That's only like 10 years. In 10 years, that glacier shrunk so much. And that change like is unheard of in time periods before this. So this is because we are altering the way that, the Earth receives like warmth from the sun, it's causing the climate to change, and it's causing glaciers like these to melt. And this is just one glacier in New Zealand, but all over the world, you're seeing things like this. Also, in this past year, a lot of areas have had really terrible wildfire seasons. Like Australia last year had its worst wildfire season. And we're seeing that now also in the west coast of the US, some of the worst wildfires that have ever happened. So we're getting really extreme events. Some of you maybe remember like 2 years ago, it was a super, super cold winter, and we called it like the polar vortex, where a lot of cities were, negative 40 degrees. So it's important to think of things in terms of climate change and not global warming, because it's not always about being warmer. It's just about things changing and not being able to sort of adapt to those changes fast enough. So we might see more extreme weather events and flooding and really crazy things. So it's important to understand pollutants, understand how they're impacting the climate, and then we can do things about that and be able to regulate emissions so that they're not as harmful. So that's really like one of the main focuses of this work.
And I assume that human activity really does affect what happens according to climate change.
Yeah.
And I think we're gonna delve into that a little bit more here in the next couple of minutes.
Yeah, so it's just important. One of the reasons why it's important to measure pollutants, because then we can change our action, we can understand how our actions are affecting the climate and be able to change those actions. So another sort of really important aspect of understanding pollution and particles and gases is that particulate matter is really small. It's like the size of, it's smaller than the size of a human hair. If you look at this measurement here, particulate matter that's less than 2.5 micrometers is like 1/50th of like the thickness of your hair. So basically these particles, you breathe them in, and then they can penetrate deep into your lungs, and they can even, the smallest ones can sort of move past the boundary into your bloodstream. And they're definitely correlated to a lot of negative health effects. Like on the previous slide, there are short-term effects like, headaches, irritated senses, coughing. People could get pneumonia and bronchitis, and also skin irritations. But the longer-term effects, people that are breathing these particles in over a lifetime, can develop more cardiovascular disease and respiratory disease. And we really want to make a cleaner planet so that people don't have to worry about these sort of illnesses, at least not because of poor air quality. So, like I sort of started to say, is that we're interested in specific sizes of particles. So the US EPA regulates different sizes of particles. So they created the National Ambient Air Quality Standards, which say that in a given area, you can only have, this concentration of this pollutant. So in our case, particulate matter, and you can't exceed that. And if you do, then you get fines, and the county really has to, crack down on businesses that are like causing the high levels of pollution, and like get them under control.
Rebecca, I have a question, if I can jump here too. How do you measure these?
Yeah, so I think that's on my next slide.
Perfect.
Yes, it is. So there are a lot of ways to measure these. So in a broad sense, the government, like the EPA, has to mandates that local areas have regulatory monitors for 6 different pollutants that they have said, it might be a few more than 6, but like a handful of pollutants that they've said, these are hazardous and we want to make sure they're under control. So in any given area, you will have at least one high quality regulatory monitor, which will measure pollutants. But one of the things that my lab works on is getting better measurements and measurements over a larger area, because if you have one instrument for all of Pittsburgh or even all of Allegheny County, do you think that that's going to represent the air quality, you know, on your street, on my street, at CMU, downtown? Like, how do you find one location that's going to represent the air quality everywhere? So what my lab does is looks at ways to measure pollutants better. So we have these instruments called the RAMPs, or that's short for, or an acronym for the real-time affordable multi-pollutant sensor. So RAMP for short. And you can see in here, there's just a bunch of wiring, and we have 5 different sensors that measure gases, and they're just off the shelf, like they're bought as is as electrochemical sensors, and they basically will respond to changes in different pollutants. And then we couple that box that measures 5 different gases with this other instrument, which is called a nephelometer, and it uses light scattering to measure concentrations of particles. So basically, it'll like take in a sample of air, and it detects how much is the light scattered and uses a correction factor to determine how many particles must be in that sample, and then you can get a concentration from that. So we basically have these devices that measure both gases and particles, and they're like, I could hold it in my hands and like carry it around. It's not too big, and we just put them all over Pittsburgh. You might have had one, you know, like in your neighbor's yard. I don't know. We had about 50 at its peak, and now we've sent a lot of those sensors to other places like Paris and Rwanda and Texas and Connecticut. So they're all over. But right now we have about 20 something of them left in Pittsburgh. And they are able to get information on pollution and concentrations of these different pollutants all over Pittsburgh.
And how do the sensors work to collect data? So
it's really interesting because some of these sensors, like the gas sensors, are they're low cost. So they're cheaper than like the really fancy regulatory monitors that the government will put out, but we're able to put out more of them because they are cheaper. So what we did at first was we co-located, which just means we put a bunch of our cheap little sensors next to one big fancy sensor. And that's a picture of one of the fancy sensors. You can't even really see it in that shed, but it's in there. And we put it next to there, and we collected data for a while between all those sensors. There were like about 20 of them up, and this reference monitor collected data from both of them, and then was able to use some like interesting like math calculations using machine learning, but it's basically just math, to get our low-cost sensors to output the same numbers, like the same concentrations as the fancy sensor. So then we were able to take these low-cost sensors and put them out all throughout Pittsburgh, and trust that they were working almost as well as a like high quality reference monitor. So yeah, it was really interesting work trying to get these sensors to work. But now we get really interesting information.
Very cool. And that's another application of machine learning, like our friends who were with us last week talked about with Emma.
Yeah. Yeah. Machine learning.
We do have a question. We do have a question in the chat now too. If it rains, do the sensors get affected, or does their data get affected in any way?
Yeah, that's a good question. So the box, like that first picture, if you saw that plastic box that the sensors are in, when we shut it and like seal it, it's watertight. So it keeps all the electronics safe. And then we take those boxes and we plug them into outdoor safe outlets or like outdoor extension cords. And then we'll wrap the connection with electric tape so that none of the wiring will get wet. We also wrap the box, even though it's like sealed pretty tight, we wrap it also with electrical tape just to make sure that things don't like get wet and then spark and short out and we lose all the data. And also what's really cool about all these sensors is that they each have a SIM card in them. So like your cell phones, they can connect wirelessly. And they basically, instead of using the SIM card to like call someone, they use the SIM card to send the data to a server where all of the information comes to. And I could just sitting here in my dining room, tap into like data from any of the sensors all over the world. So it's pretty cool.
So is that information live then?
Yeah, it is live, and we're gonna look at some of that later too.
All right.
Okay, cool. So here are just some sensor sites in action. So as I said, they're like all over Pittsburgh. This one's at someone's house. This is me putting one up. Actually, it's at the same house, but back to the grad school being really interesting, get to climb ladders and get outside, not in front of a desk all day. So, well, now more so in front of a desk, but you know. Here's a cool sensor that's really right downwind of the Clarendon Coke Works plant. You can see it's basically looking at the Coke plant. So we'll get really high concentrations, in areas around the Coke plant, which is pretty interesting to see.
Cool. And it looks like we've got a question in the chat. How much do the low price sensors and the fancy sensor cost?
Yeah, that's a good question. So the really like the EPA regulatory monitors will be like tens of thousands of dollars, and our low cost sensors like all together might be like $1,000 or $2,000. So it's like orders of magnitude lower. They're not super cheap in and of themselves, but just in comparison to the like tens of thousands of dollars.
Very cool.
Yeah, but good question. It's good to have a sense of what we're talking about when we say they're lower cost. So one thing that's been really cool, like I've mentioned, that we were able to put out about 50 of these sensors all throughout Pittsburgh. And this is what I've spent a lot of time in grad school, is looking at the data from these sensors. So, maybe you could look on here and see like, oh, if you live like near one of these, or, some location jumps out, that might be interesting. But we specifically put them in areas where that have like sort of different emission profiles, like different sources that we'd expect to see like high emissions. So like we have some that are around a highway, and some that are like in just like sort of more urban sites where you might have restaurants and also emissions from cars. And then we have these more like suburban sites all in green. So you'd expect lower emissions there, like lower counts of particles there. And then we have areas that are right near a steel mill. We have some sensors that are right near the Coke plant. So it's really cool to see how these pollutants change over time and space.
And maybe we could real quick ask folks in the chat to throw in, where do you think the most concentrated pollutants will be on this map? And you can go ahead and throw your answer in chat. Okay, so we've got some folks are thinking downtown, near the factories.
Yeah, those seem like good guesses.
Yeah, near the steel mill.
Yeah.
Very cool. So Rebecca, where do you think the most concentrated pollutants are?
Yeah, so I think like definitely those were good answers. Downtown, you will see more in certain areas of downtown, and we'll even see differences in different parts of downtown. because you can have certain streets where like the buildings will sort of trap pollutants better than other areas. So that'll create like higher concentrations. Definitely downwind of the factories like the steel mill and the coke plant, we see higher concentrations. Those are the highest most of the time. But what's really interesting is that it's not just about how close you are to a source, it's which direction you're in. Because these sites that are light blue down by the coke plant, they have, pretty much background level concentrations of pollutants compared to the red sites that are east of the coke plant. Why do anyone have an idea why that is? You can write it in the chat. No guesses? Or no, now people are. Yeah. So we see Alex said that the wind is blowing east. So yeah, here the wind generally blows, like you can see from this arrow, in the northeast direction. So the sites that are just downwind of the coke plant actually more often have higher concentrations of different pollutants than the ones that are just on the other side. So it's interesting when it comes to like thinking about community health and like what communities are like most affected. So it's interesting to think about like the spatial differences. And this sort of goes back to the idea that if the EPA only has, 2 sensors in this whole area, how do we know what people are actually exposed to? So it is important to have like a lot more information than we would get. And to illustrate that point further, let's see. Oh, to illustrate that point further, I'll show you another plot in a little bit. But first, here are just some pictures of the coke plant. Here you can see more emissions from the coke plant and just a pretty like sunset, which also a fun fact, maybe a positive of particulate matter pollution, if there is one, is that it creates really pretty sunsets. So because you end up with more sort of like light scattering from those particles, that sometimes you do get nicer sunsets. So that's something that we experience here in Pittsburgh. That's nice. But yeah, and here's more measuring, and that's the drone again. But like more measuring of these emissions around the coke plant.
And you say in your title here that you're interested in quantifying the emissions. What does it mean to quantify the emissions?
Yeah, so it's one thing to, look and see that, oh, it looks like there's smoke coming out of the coke plant, or like smell something and be like, oh, it smells like rotten eggs. There must be something being emitted right now. But we want to know how much is being emitted. So quantifying something just means putting a number on it. So that's why it's really important to have all these measurements so that we can understand how much of which pollutants are being emitted when, and then where does that have an effect on people, and how much of an effect does that have on people, and then ultimately be able to go back and say, we need to get these emissions down by this much, and that'll affect human health by this much. And then people in government can make policies that will put that into action. So here's one result. This is a lot going on this plot, so maybe we'll break it down a little bit. These are basically all the locations. So if you look along the x-axis, so basically like along the bottom where my arrow is, you guys can see my arrow, right?
Yep.
So these are all the different sites from site 1 to site 42, and they're grouped. If you look at each of these boxes by color, so we have these 2 sites that are downtown, and then we have these sites that are in the urban residential area. So back when we looked at the map, that's like where these sites are. One at a highway, a bunch in like more suburban areas, which might be more similar to where you guys are living, or a bunch of you might be. Then we have 3 sites by the steel mill, 3 by like downwind of the coke plant, or upwind of the coke plant, and 3 downwind of the coke plant. And you could see that the green bars are like the percent of time that the air quality is really good. Like the number of hours, so we look at all the hours we were measuring, and then we look at the percent of time that it was under a certain level, which is like, we measure in micrograms per meter cubed, which like might sound confusing, but it's basically a weight, like how many particles in a certain amount of space. So the green bars are hours where it was totally fine, like really low concentrations. The yellow bars are, you know, they're smaller than the green bars. So I guess the first big takeaway is that all throughout Pittsburgh, most of the time the air quality is pretty good. So that's something you could like sleep well tonight and be like, okay, most of the time it's pretty healthy. So don't get all concerned about it. It's pretty okay. Then the yellow bars are hours where it was between 12 and 25. So that's like a little bit higher. Maybe if you have asthma, maybe you'd have like a little cough or something. But then these orange and red bars are ones that are really high, where either the EPA, so the US regulatory agency, or the World Health Organization, which again, you probably have heard a lot about if you have heard people talk about COVID, but the World Health Organization sets like health standards. So they have slightly different markers for like what is hazardous. But if we look at, you know, both of those, the red and orange markers are hours, like percent of time where it was really high. Everyone agrees that it was really high concentrations and like not good to be breathing that in all the time. So one thing that we notice here is this one site. This site sort of jumps out. Why is this one? Anyone have any like guesses? This is a downtown site that has a lot of hours where we have bad air quality, where there are a lot of particles. Anyone have any guesses why this is so bad? Oops. Oh no, we went backwards. Yeah. Okay, there we go. So someone says traffic. That's a good guess. Someone says near factories. That would be a good guess too. What's like, focus on the fact that, see, it's in this this black box that says downtown. So we don't really have any factories downtown that I know of anymore. There used to be, so not factories, but that's a good guess. No trees. That's interesting guess. So one thing, someone said traffic. Downtown does have a lot of traffic, but then the question would sort of be why is site 1 like so much better than site 2? Lots of people do emit, you know, particles, but good guesses. And someone said wind. Maybe it's just like in a bad direction. One of the reasons we actually found out is that this site is right near a restaurant, restaurant exhaust pipe. I think Dr. Websterwood we were talking a little bit about this beforehand, about like, there's this one picture that my advisor shows where we're like measuring right at the exhaust of a I don't know, right at the exhaust of a restaurant. So there's a lot of restaurant cooking emissions right there. And like, you know, you walk by a restaurant and you smell stuff, like that's an indicator that there are things being emitted into the air. So that's why that site's really bad. Someone asked what does the star mean? So I think you mean this little diamond right in the middle. So that is the mean concentration. So it's like the it's the mean concentration. So it's the average basically over the whole sampling time. Good question. And then the last thing I want to point out here is if we look at the 3 sites in this red box by the east of Coke plant site. So they're downwind of the Coke plant, and you can see that their red and orange bars are bigger than the sites that are west of the Coke plant, and they're the same distance. So that's an interesting sort of observation when it comes to like direction really matters because the wind is blowing. And basically the people living east of the Coke plant are, you know, more susceptible to having, you know, different health problems because of this. So it's something to really consider. How can we help those people there, right?
Mm-hmm.
So yeah.
And so we know that a lot of these particulates can come from traffic and factories and restaurants, right? So I think I'm going to hand things back over to Kristen. I think we have another poll, right?
Mm-hmm. Okay, wait. And yep.
Indeed we do. So as you all probably are aware, during COVID-19 shutdowns, we didn't have as many particulates going out into the air, but we want to sort of get your thoughts on this. How do you think the pollution levels changed here in Pittsburgh during the COVID-19 shutdowns? So I'm going to go ahead and launch polling now. Do you think that they A, increased, B, decreased, or C, stayed about the same? I'll give you a couple of seconds to answer here. And this is something that, you know, I happen to think about as well, as I'm sure many of you did. So we'll see what the final answer is. I'll give you just a couple more seconds to put in your response. All right. So Rebecca, it looks like our majority answer is that the pollution levels decreased during the COVID-19 shutdowns. So what is the actual answer?
Yeah, so I will say, for one, it was a little bit of a trick question. I guess I like trick questions, but I just said pollution levels. I didn't ask you what ones. So yes, we've been talking a lot about particulate matter. And for that, you're all really correct, that, or most of you are correct, that, yeah, it decreased because you have a lot less sources emitting, right? You have less people driving to work. You have less people, you know, restaurants were closed. Factories for some portion of time were a little bit closed, but we'll talk about that. But yeah, so in terms of particulate matter, there were big decreases, or at least like significant decreases, but there are other pollutants that in some areas did increase because we have a lot of complicated chemistry. So things like ozone might have increased in some places because there weren't other pollutants to react with it for it to go away. So chemistry is pretty cool, and especially atmospheric chemistry, there's a lot going on. So for the most part, yes, the shutdowns did decrease a lot of pollutant levels, but the one person who wrote increased wasn't really wrong, because I didn't specify which pollutant. So, you know, there was a deeper level to that question. So good job. I'm just going to highlight a little bit of, we have, you know, Rita, it's okay to take a few more minutes to highlight some recent work here. So like I said, we have this network of sensors that report, you know, to a database automatically. And it was a really good project to work on when, you know, campus was closed and my lab was closed and I couldn't go in and do more work. So I got to look at the changes in pollutant concentrations with the COVID-19 shutdowns. And I'm sure a lot of you maybe have seen pictures like this, where, you know, pictures from all over the world, where you have, like, on one side, this is what it used to look like, and this is what it looked like now that people aren't driving everywhere, and like it's so much clearer and all the haze is gone. And we've seen that like all over the world. So we were curious what it looked like, what the actual numbers of pollutants looked like here in Pittsburgh. So here, this is another plot, and I'll walk you guys through it. So this is a lot of, you know, what I get to do with the data we collect, is like thinking of ways to picture it and visualize the data and make sense of it. So here we have, you know, going from 0 to 20, but it really goes to 23. It's the hour of the day. And then on this y-axis are the particulate matter, PM 2.5, the particulate matter concentration. So you could see over the course of the day, you start midnight, it's pretty low, and then it increases in the morning. Why do you think, anyone know why it's increasing in the morning? What's happening here? And this is just, at sites where there's a lot of, let's see in the chat. Morning rush hour, people going to work. And let me specify again, this is before COVID. So this is like a picture this is data from before COVID. So you're right, it's morning rush hour. People get in their cars, they make some breakfast. We have like a lot of emissions going on from that 8 to 9, 10 o'clock slot. And then in the afternoon, because again, the atmosphere is really complicated, it gets lower than it was at night. And that's because the atmosphere sort of stretches up and it's really big. This lowest layer of the atmosphere is the biggest in the middle of the day. So when you have a lot of space and the same amount of pollutants, your concentration goes down. So you have lower concentrations in the middle of the day. And then we see another little spike here, which is again, people driving home from work, right? So that's what it looks like at sites where there's a lot of traffic. So like downtown, by the highway. But if we look at sites where there's industry, like near the Coke plant and the steel mill, we see a little bit of a different pattern where the pollutant concentrations, you can see they're higher overnight. Anyone have any guesses why they're higher over here overnight than in the high traffic sites? Any working later, runs overnight? Yeah, so it's a mix of the fact that these factories run overnight, so they're emitting particles overnight. And the really interesting thing is, again, it has to do with the atmosphere and how the atmosphere works, is that it sort of scrunches down. And so that lowest layer of the atmosphere, called the boundary layer, scrunches down at night. So you're smushing whatever pollutants are around into a smaller space, and then you have higher concentrations. So you have more emissions and less space to put them in, so you get higher concentrations. So what was cool, what we could see with our sensors, I'm going to show you data. These were from March 2019, so like last year. And now I'm going to show you data from this March. So same time, it should look the same, but obviously the world was very different. And this is what the concentrations looks like at those high traffic sites. Isn't that cool to see that you could see that visual drop in pollutants throughout the course of the day. Let's see, there's a thing. Oh, wow, we're getting woes. Good. It is cool that you could really see that change. And that was all throughout Pittsburgh, that at least, not the industrial sites, all throughout the residential sites, you could see that decrease. And you don't even see any change throughout the day because people aren't going to work. They're not emitting any pollutants there. Oh, wait, let me see. Yeah, but here, what's interesting is if we look at the industrial sites, they did decrease, but not as much as the high traffic sites. And if anyone remembers, there was a list of businesses that were called put on the government's essential businesses list by the governor for the state of Pennsylvania. And although at first the steel industry was not on that list, so they weren't allowed to be open at first because they weren't on that list. So when everyone was closed, steel industry was supposed to be closed, but they petitioned to be put on the essential business list, and they did get on it. So we could see that they were still emitting during this time, but maybe less than they would normally be because maybe they had less people working, or it's interesting to be able to see that in the data. So that's one thing that's really cool about research is you put all this work into getting data, and then you can get an interesting story from it.
And
so,
Becca, we've got a question came in chat.
Mm-hmm.
How big is the group that you're part of, and how do you get the money to buy your equipment and sensors?
Yeah, that's a cool question. So I really enjoy the group I'm in because it is really big. My lab, which is called CAPS, it's the Center for Atmospheric and Particle Studies, is made up of 8 different professors. So a lot of lab groups are one professor and their students, but because all 8 of these professors have very similar work. They've decided to like work together and collaborate on a lot of projects. So each of them have about, like maybe 5 grad students. So, or so, give or take. So there's maybe like 30 PhD students in the CAPS group. So that's a lot of people. Not all of us work on this specific project. There might be like a subset of like 5 people working on this project. And we get the funding, part of being a professor. So this isn't something I'm super familiar with, but maybe Dr. Webster could like, expand on it if she wants. But basically professors have to write grants to get money to do their projects. So specifically, that's as much as I know about it, but specifically, we get a lot of funding from the EPA, so from the Environmental Protection Agency, because we do a lot of like environmental work. So yeah, if you want to add something to the getting money part.
No, that covers a lot of it, right? It's a lot of writing. You tell cool stories about the science you want to do, and if the government likes it, they give you money to do the science.
Yeah, it's fun stuff. Okay, so see that. Okay, so basically I think we're getting to like the last slide or so of my portion, but you can see like there are a lot of interesting ways that we can measure pollutants, and we want to ultimately like fully understand emission sources. So like I talked a lot about cars and factories, but there are a lot of different sources out there. So that's why, in my work, I've gotten to measure emissions like straight from vehicles like this F-150 there. You see me, I'm really little there in that picture, not like little in age, but little in size of the picture back there, measuring emissions from a vehicle. I've obviously spent a lot of time measuring emissions from this Coke plant. And now, which I didn't talk about at all, I'm actually doing a lot of lab work looking at more like household products. So like paint. So like you can see there, like paints emit a lot of organic compounds, which then go to like end up creating particles in the atmosphere. So there are people looking at like sunscreen and perfume and household cleaners and how do those emit particles into the atmosphere, and what are the effects of those. So we want to be able to understand where are pollutants coming from, how do they change over time and space, and that will be able to inform policy and be able to make cleaner, safer air for us and everyone around. So it's been really cool work that I've gotten to do so far, and I look forward to getting to do some more. So yeah, with that, we're gonna jump into, I think, talking about our activity. I don't know, I think, yeah.
Yeah, so our activity is going to be about dispersion and I guess diffusion as well. But we're not going to be using air. We're going to be using water in this case. And we're going to be using food dye to see how it can sort of spread out in the water and how it's affected by different temperatures. So sort of like Rebecca was talking about earlier, how we're able to see how the different temperatures can affect the level of pollution in the air. We'll sort of be able to see how the temperature of the water is able to give us different results. So with that, I'm going to pass it over to Saul, and he's going to give us a quick outline here of our activity. And then after that, we'll go into our 5-minute break. And then we'll come back and go off into our breakout rooms and do the actual hands-on activity and experiment.
All right, awesome. Yeah, so can we go to the next slide, please? I think there might be an image that's going to pop up. Yeah, so you guys might have seen or had the chance to do your activity where you put sort of Vaseline or petroleum jelly on a paper plate and then sort of hung it up for a couple of days. So you might have noticed that depending on where you were, you got different amounts or different levels of sort of particulates accumulated on the plates. And so I think this is now the time where we want to talk about that, I believe. Or do we want to just jump into describing the activity that we're going to do right now?
Yeah, so let's just jump into describing the activities.
Okay, fantastic. So in terms of the activity that we're going to be doing today, it's all about diffusion and how sort of the temperature of the environment where things are being diffused has a big effect, or maybe it doesn't have an effect. And so the idea here is we're going to put food dye into water of different temperatures, and we're going to see how the different temperature of the water affects how the food dye sort of moves through the water. And we're also going to introduce cardboard into 2 different temperatures of water and see how the food dye is able to sort of permeate into this cardboard. Yeah, it's going to be exciting stuff. You can sort of, during the break, you can think about what you think will happen in terms of the temperature and how the food dye moves around.
And then towards the end, when we come back from our breakout sessions, we'll talk about potential reasons why that dye would have been more attracted to, or maybe less attracted to, the cardboard. So for these activities, you'll need some sort of container, like a food storage container works well because it has transparent sides usually. But you can also use like any type of bowl. Plastic is preferred. And then we'll be starting out with cold water first. You only need a small amount of cold water, maybe like a cup of water or so. You don't need gallons and gallons of water. And then we'll do the experiment with the dye and the cardboard. And then after that, you'll dump it out carefully into a sink, and you'll get some hot tap water. It'll only be like hand washing hot tap water, just so you know. And then you'll do the same thing again with the hot water. You'll also be able to check out a Pittsburgh air quality map, and maybe you can make a hypothesis about some of our paper plate collection results that you'll be able to see as well during the breakout session. So we do have a question I see. So cold water and clear bowl, yes, that is what you'll need, and you'll need food coloring or food dye, however you like to call it. And right now I have 5:50 on my clock, so we will go into our 5-minute break now. And then, so anybody who needs to take a break, get up, stretch, do whatever you need to do, come back at 5:55, and then everyone will be split out into their breakout rooms at that time. So I'm going to go ahead and stop the recording now. All right, so welcome back, everybody. I hope you were able to learn a bit more about pollution and also diffusion. You should have gotten to take a look at the Pittsburgh air quality map, and hopefully you were able to draw some conclusions between that map and maybe our air particulate collector paper plate activity results as well. So now I'd like to ask, if you were able to do the diffusion activity, how did it go? You can type your response in the chat, or if you would like to share a video, you can also do that.
It looks like Allison G has raised her hand to share.
Okay.
So I already put away my stuff, but it looked like for the cold water, the food dye moved a little slower than versus the hot water where it moved out and it moved a little faster.
Okay. How about anyone else? Would you like to share your results? So I see in the chat here, so he said that the dye in the hot water spread more quickly than it did in the cold water. So that's sort of similar to Allison's results. And then Malachi said, I only had coated cardboard. So your results might have been a little bit skewed in that case. So how about Rebecca? Can you tell us in the diffusion activity what the significance of adding that cardboard would be? Like, what does that cardboard represent if we are talking about pollution?
Yeah, I think that the cardboard was there to represent like obstacles along the for diffusion, right? Is that I feel like, yeah. That like you'll have buildings or you'll have like mountains or other sort of like land features that'll like determine where pollutants will move beyond just the wind direction. So for example, in Pittsburgh, you have pollutants coming up from the coke plant and the steel mill, following sort of the riverbed and also some of the valleys, because it's just sort of the easiest path for them to travel in.
The path of least resistance. Mm-hmm. And then is it also true that, you know, we have that piece of cardboard there, it's also a surface for pollutants to collect on as well?
Yeah, that's definitely like a good analogy. And I like when you have a lot of pollution, it'll sort of like fall out because these are particles, right, suspended in the gases. So sometimes you'll have soot like sort of fall out, and like back in the day, if your grandparents are from Pittsburgh, they might be able to tell you stories about going to work in a white shirt, and then by the middle of the day it being like gray and sort of like covered in soot from all the pollution that was out when there were more steel mills all around here. So that might be interesting to ask if you guys are from Pittsburgh, like families back a few generations, asking maybe grandparents like how the air quality was back then. Yeah, because you could get those pollutants sort of like falling out and condensing onto like shirts or windowsills or onto buildings or things like that.
Exactly. So lastly, we want to ask you in our poll, and this poll will be one that you can answer in the chat. What are some of the ways that you can minimize your impact on air quality? So based on everything that we've learned in our session today, what might be a few ways, or even one way, that you might be able to reduce your impact on air quality?
And you can write it in the chat. Yeah, we see one person wrote an electric car. That's interesting. You can ask your parents to check their car so it's not producing fumes. Yeah, there are regulations for vehicles, and you actually have to get your car checked every year. For like, I think it's every year here in Pittsburgh or like in Pennsylvania. So that's making sure that you're under a certain amount of emissions. Get a Tesla. Those are cool cars. And just to make it clear, like when people are saying electric cars and Teslas, they are really good options because they don't run on like coal-based fuel and they don't emit anything into the atmosphere. So those are good. They are, some of them are expensive though. So it's,
Definitely.
are there more things that like so you guys aren't buying cars right now. So what are things that like, you know, maybe you could do without buying a car? So don't drive around just because you want to. Yeah, probably a good option. Maybe like choosing to walk instead of drive if you know you're going somewhere close. Riding a bike. Yeah, we see walk or bike more often. Great. Just even those little things like choosing to not use the car when you don't have to. And also even like shutting off lights because we get electricity from like often like plants that are powered by fossil fuels, and those plants emit other pollutants. So you, by not wasting electricity, you'll be polluting less. So remembering to shut off lights when you're not using them, that might be a good option. Or yeah, not leaving things plugged in that don't need to be plugged in.
Yeah, exactly. Those are all good ways that we can try to reduce our impact on air quality. I think right now we'll move on to second to last slide here. Does anybody have one final thought, question, or comment? And then also I'd like to remind everyone to please complete our post-session survey. It's going to be available on Canvas, should be available now, and it will be available for 1 week after this session. Feel free to raise your hand if you have any questions or comments.
Looks like we've got a question in chat for Rebecca. How did you know that this is the problem you wanted to solve or help with?
Yeah, that's a good question. I think like a lot of the experiences I had before grad school, in that I was, you know, working on things that, like I said, when I was doing the waste to energy sort of research, I saw that like measuring pollutants was pretty interesting. And I wanted to do just generally something that would have like a positive impact on, you know, the environment and humans. And this, it's not necessarily that I was seeking out this problem, but I was looking for something generally that would be positive, like for the environment and for people. And this sort of fit both those categories. And it's when you're looking for a lab to do research in as a grad student, you need a lot of different factors to sort of line up. So it was a good location at a good school with a professor that seemed pretty cool. So it just seemed like all the pieces fit into place. And someone asked if when I leave Carnegie Mellon, if that's a when. No, that's a good question. Basically, I'm hoping to graduate this year. So I've been here, this is my 5th year. So I'm really excited to be hoping to graduate in the spring. So hopefully it's a when I leave. Thank you for the good luck. But what will I work on? I really don't know. Right now I'm applying to jobs, and some jobs are in industry and like consulting with like government agencies as like a air quality specialist. Those are some jobs I'm interviewing for, and maybe I'll get that. Maybe I'll stay in research and like research a slightly different problem. A lot of times people graduate from grad school and then do a postdoc where you like maybe do research that's maybe similar but a little different. But I think I want to stay doing I know I want to continue doing something that'll have a positive impact on, you know, the environment and on people. So it's a good question. You know, maybe in a few months I'll have a better answer.
All right. Well, thank you everyone for participating today, and all of our middle school students, all of our mentors, our coordination team, and especially Rebecca for taking the time to teach us a little bit about your research about air pollution and how we can try to reduce our impact on the air pollution issues. So
Thanks.
thank you again for joining us. Thank you, everyone. And we'll see you next time.
Thank you. Bye.
Bye.